Hello, class. Welcome back. Today is lecture 17. Today we are going to step it up with some step functions. So these are very useful functions, and Laplace transforms help us deal with them when they're involved in differential equations. So this is where the power of Laplace transforms really comes into play. So first of all, you may have seen these before, but may have not. So we are going to talk about what they are for a little bit before we worry about differential equations. So what is a step function? It has a couple other names too, but I'm just going to stick with this name. Well, step functions are based on the following function. What you want to sort of think about as a switch, some sort of switch that's either on or off. So we're going to think about it as being off before some time given by c, so some number. And then on after. So in real life, there's lots of things like this. So it's good to have a function that models this sort of situation. And it's going to be written as a piecewise function because that's really what it is. And what we do is we use a subscript c to indicate this time at which the switch turns on. And it's a function of time. So this is the name of the function, u sub c of t. And what it is, well, what is it? What would we think of as being off? We would think of that as like being the number 0, like nothing is happening, so it's off. And it's a piecewise function, so piecewise functions, you define what they are on the left side, and then when they are that on the right side. So if time is less than c, that's when it's off. And then on is going to be a 1, and it's on after c, or equal to. We're going to put the equal to on the c. So this is called the unit step function. And we can use it to build lots of other step functions. So basically, step functions are just functions built from this guy. That's the idea. So what does this thing look like? Not so hard to visualize. There's this time c, and before c, we're really just going to go to 0. We're not going to bother going to the left because we're always thinking of this as time. Before c, it's just stuck at 0, but then after you get to time c, it's 1 forever. And remember, this open circle indicates that it's not touching that point. It just goes right up to it. So that's how the graph looks. And then using this, we can create lots of other step functions. So let's do that next. So this is sort of like a building block. We just use this one in a bunch of fun ways. So for example, if I multiply the step function u sub 5, then what is this really? Well, now what's going on is that when it's on, it's not just 1, it's 1 times 2. But when it's off, it's still 0. And then this 5 indicates again, when does it turn on? At 5. So before 5, it's off. After 5, it's on. And so the graph looks something like this. 1, 2. Here's 5. It's on after that. And it's off before that. We should use a different color, but that's okay. Okay. You can do some negative stuff to make it a little bit different. So for example, negative 3u2 would be, let's just jump to the graph. So until time 2, it's 0. And then the output is -3 after that amount of time has passed. So it looks something like this. I should use different colors than the axis so it's more clear. It looks something like that. Okay, and you could write it piecewise again, but we're going to get used to not having to describe it piecewise. We're just going to be able to see that and know exactly what it looks like. So let's try to do that right away. So you can get very complicated. So this is a step function. So first, let me just draw the graph. And then afterwards, maybe try to describe it. So let's see, 1, 2, 3, 4, 5, 1, 2, 1, 2, 3, something like this. So you could have something that sort of takes little steps up after each unit of time, something like this. It's an interesting step function that just jumps up by 1 after each unit of time. And I can describe this using step functions, using the unit step function in a bunch of different ways. So how are we going to do that? So it's a bit tricky, but the idea is that we're just going to go from left to right. So starting here, what's the value of the function? It's -2. And then it stays as -2 until it gets to time 1. So what I need is for it to go up by 1 after this happens. It needs to jump up by 1. So if I just add U1, that will accomplish this. So if I just leave it like this, then the graph I've got is this, basically, this blue stuff. But of course, that's not what I want. So, but first, let's see if you understand this before you move on, because what's happening is I'm starting at -2, and then once 1 unit of time has passed, I add 1 to that -2, which brings me up to -1, which is where I want to be to get to that blue line. But now what if I want to keep going? So forget all this. I want instead to jump up another unit after another unit of time so that this happens. Well, then I'm basically just turning on another switch, but that switch happens after time 2. And so you can sort of see the pattern here. After each unit of time, I'm adding another switch that turns on. So that this U3 will get me to here. And then I'm going to need U4 to bump me up at time 4. And then I'm going to need U5 to bump me up one more time at time 5. And then the pattern will just continue if I wanted to go further. So that's the idea. Maybe actually, let me do one more interesting one. So let's jump down here. Let's do one more actually. So at time 6, it's going to jump back down by 2. So then what would I have to do? Well, now I need it to jump at time 6. I need to take away 2 to make it jump down 2. So I need to subtract 2 switches at time 6. And that'll give me that. Okay. So you can do lots of cool functions like this that model real life things of switches turning on and off. So you can get like a periodic thing going on where it just sort of jumps back and forth. And you could do this as far as you want to go. And you could do this in the same way. So what would this be? Well, let's say if this was at 3 or something, then you're starting off with 3 and you're subtracting 2 at the next time. So this would be, if I'm counting, just change it up a bit. So let's pretend this is 2, 4, 6, and so on. So I'm subtracting 2 to get me to jump down to 1, and that's happening at time 2. So that's going to be a 2 there. And then when I get to time 4, I want to jump back up by 2. So I got to add 2 of those switches. But then when I get to time 6, I want to jump back down. So I got to subtract 2 more, and so on like that. Okay, so this is the idea behind step functions and interesting ways in which they're used. We can also combine them with more familiar things. So let's see that too. So we can combine step functions with more familiar functions that you're like super used to using. So things like t squared and stuff like that, or sine of t. Oops, I should have put the name on the right. That's okay. G of t will be sine of t. So the idea is that you can take these functions and you can make them start at a different time. Instead of at 0. So for example, f of t, that's the parabola. And if I'm just looking at positive time, just look something like this. But what if I wanted to start at a different time? Well, all I have to do, if I wanted to instead say start at time 5 and do the same thing, what I'm saying is I want it to just be 0, 0, 0, 0, and then all of a sudden turn on like that. Then what I need to do is shift the function to the right by 5 by subtracting 5 on the input. But then in order for it to stay at 0 until that time 5 happens, I need to multiply it by this switch function. So what this is doing is it's saying before you get to 5, everything is just 0. But once you get to 5, it becomes this function. And so we could do the same thing with like sine of t. Let me do cosine of t just to, actually I am going to go back and change all that. G of t will be cosine of t. If I could write correctly, there we go. So cosine of t looks something like this. If you remember from back in the day. Whoops, that's too sharp of a curve. That's okay. So that's one period of cosine. So if I said, well, I want it to start at pi instead, then if I just shift cosine by subtracting pi and multiplying by the step function at pi, then what will happen is it'll be 0, 0, 0, 0 until you get to pi. And then it'll jump up and become cosine. So I guess now this would be 3 pi. Okay, so that's the idea. So we're going to play around with things like this a lot. Up next. All right, so now how do Laplace transforms interact with these things? So this is where Laplace transforms really come in handy, because if you use these functions in your differential equations, they're a bit hard to deal with. You'd have to deal with piecewise things. which would be a bit annoying. Okay, so let's see it. Given a function, and it has a Laplace transform, pretending it already has one. So the Laplace transform we can call f of s because it's a function of s, and it's just this. Then what happens if you start the function later, aka what is u, the unit function, unit step function, starting at time c times the function shifted over by that amount. This is what we want to figure out. And it's actually pretty interesting. So we'll use the definition. So definition of the Laplace transform is you just take this thing and you stick it in this integral. And then you see what happens. Well, what happens is that the inside is 0 until time c. So what that means is you're just integrating, you can think of it, the integral as area again. So what's the area under 0? It's just 0 until you get to time c. So this is really just the same as starting the integral at c, because before that, there's nothing there. And then integrating this, because what's happening is that this piece, after you get to c, the definition of this thing is just 1 times this thing. So 1 times that thing is just that thing. And so now this is the integral that we're dealing with. So then if we just do a nice little change of variables, so I'm going to let v equal t minus c. And then t, if I just add the c over, will be v plus c. So that'll come in handy too. Then I change variables. This will be interesting. So what's v starting at? So remember, you have to change your limits of integration. So what does c become when I change everything to v's? So when t equals c, v equals c minus c equals 0. So that's why this is going to be starting at 0 now. Let me do this change of variable. Up here, this t becomes v plus c, and f of t minus c just becomes f of v. And then dt, well, if I take the derivative, if I do the little dt trick, this is just dv. C is just a nice constant number. Don't have to worry about that. It goes away and becomes 0. But this, I can take out the negative sc, and because this is an integral in terms of v, and this thing has no v's in it, I can just pop it out to the front. And this is just the Laplace transform now. This thing, that's just the definition of the Laplace transform of f of t, except we change the letters, but it's still the same. If I just change the letters back to t now, it's the same. So this gives us a nice little formula, which says basically that if you have a function which is starting later at time c, that's what all this is saying, then the Laplace transform of that is the Laplace transform of the function, but you got to now multiply it by this extra e to the negative sc, where c is the amount that you're shifting over by. Okay, so let's just calculate some things real quick, just for practice, using this formula. So let's calculate the Laplace transform of 4u6 of t plus 3 times t minus 4 cubed u4 of t minus 7 e to the 5 minus 2t times u2 of t. And now we're going to use this rule. The Laplace transform of uc of t times f of t minus c. I can use this formula. So the key is that to use the formula, you have to have the function shifted over by c matching the same as the step function. Okay, so first step is remembering that the Laplace transform is linear, so we can pull out this constant and we can separate a bunch of stuff just to make our life a little bit easier first. So let's do that. Oops, I forgot the u. Very important. That's the whole point. And then for some reason I put the u second, but now I'm going to switch the order of multiplication just to make it look the same. And same thing here. Okay, so now working from left to right here, what is the Laplace transform of this thing? Well, it's not, it doesn't look like it's in this format, but it secretly is. It's because you can think of this step function as being multiplied by 1. And so what's going on is that my f of t is just a constant function 1. So then if I shift it over by 6, which is what I need to do so that it matches, because this is a step function starting at 6, well, what happens if you plug something different into the constant function? It still doesn't do anything. It's still 1. If you plug in 100, you'll still get 1. If you plug in 1,000,000, you'll get 1. If you plug in t minus 6, you still get 1. So then, according to this formula, this is 4 times e to the negative 6s. So c is 6 in this case, times the Laplace transform of what's my f of t? 1. And that we can remember, or we can look it up in a table, and it's going to be 1 over s. That's what that was. Okay, so that's that one. This one, so it's already set up nicely. It's 3 times e to the negative 4s, because c is 4. And what function is being shifted by 4? It's t cubed, because if I plug in t minus 4, I do get this exact thing here. So according to this formula, it's e to the negative 4s, because c is 4, times the Laplace transform of t cubed, not t minus 4 cubed. The whole point is that you're calculating it without the shift. And that, do I remember that off the top of my head, or I'm gonna have to look it up probably. Look it up later. But anyway, you would use the table. So this you could just look up in a table. Don't have it handy. All right. Now this one is the tricky one. So the idea is that this is not in the correct form. Let's do some scratch work over here. So this is not in the correct form, or it's not clear that it's in the right form. So here, what's C? C is 2, because I'm trying to shift by 2. So that means that we need the function to secretly be the result of plugging in t minus 2 to something. But it's not clear what that something would be. But luckily we can figure it out. It's a bit tricky though. So the idea is I need to know that when I plug in t minus 2, the result ends up being 5 minus 2t. So I need to know a number that I'm multiplying t minus 2 by and another number that I'm adding, and that this needs to be e to the 5 minus 2t. So I'm just going to solve for a and b here, and that'll do it for me. So it's just a little system of equations. So a times t needs to equal -2 times t. So a has to be -2, and -2a plus b needs to add up to 5. So then I already got a, plug that in there, and you'll get b equals 1. So that tells me the function that if I plug in t minus 2, it'll become this thing. Okay, so f of t equals e to the -2 t plus 1 will result in, if I plug in t minus 2, it'll be this 5 minus 2t that I want. Okay, so a lot of little algebra tricks to figure out that this. So now I know my c is 2. This is going to be e to the -2s times the Laplace transform of, so what is the function that I had to plug in t minus 2 to get me this thing? It was, as we just figured out, e to the -2t plus 1. So then, once again, you would finish this with the table by using the table. So this Laplace transform, you could just use a table to figure out. Okay, so then once you did that, this would be the answer here. I'll leave those blank. Oh, whoops. We already figured out. We did figure out this one. This one I remembered. Okay. I think I can remember this one. It's like, I think it's going to be like 3 factorial over s to the 4th, if I remember. Right? But the other one I can't remember. Okay, so use the table. All right, so now sort of get an idea of how these work. We'll get more practice with it. But to continue moving on, how do we now use what we just learned? Well, we can now solve an initial value problem the same way we did last time, using a Laplace transform on both sides. But to do that, we need to know how inverses work. So we got to think about inverse Laplace transforms with step functions. And so the idea is basically, if you end up with a function of s and you have this factor times some other stuff with s, then this is going to tell you that the inverse Laplace transform is a step function of some kind multiplied by something, because this must have come from a step function. Okay, so then we can find the inverse to get f of t equals something, and it's going to be a step function. Okay, so let's see an example. So we won't jump into solving a problem, but we will just calculate some inverse Laplace transforms for some practice. 1 over s minus 10 e to the negative 3s. How about that? So the idea is I'm just going to use my formula backwards. So what I can do is I can write this inside business as the result of some Laplace transform, because that's what it is. Let me write it in the same order as the formula. And then the stuff that's not the e part, that doesn't look like it came from the unit function, I'm just going to rename that to be something else, like g of s. So then the inverse Laplace transform that I'm looking for is really the inverse Laplace transform of this e thing that's going to correspond to a step function times the rest of the stuff. But what does this really mean? So remember how the inverse Laplace transform, what it really means is that if I take the Laplace transform of the stuff in the inverse, it goes back and forth, that, wait, sorry. Let's do it like this. So it means that I must have had a step function starting at 3 times some function shifted by 3 for me to make this appear. And that is what's going to equal this inside of the inverse. And so what I'm really looking for is what is this function? So there's some function whose, I took the Laplace transform and I took the Laplace transform of it shifted by 3 times the unit function starting at 3, and it turned into this. And what do I know about this? Well, I know that because of that formula, the Laplace transform of this g is this thing. Let me remember what it was. It was 1 over s minus 10. So this is getting a little cyclical. The next example, I think, will make it a little bit easier. I think I've overused notation, but let's just finish it. And then the next example, I think, cleared up a bit. So what do we need? So we need to know the inverse Laplace transform of 1 over s minus 10. And that will be this missing g of t function. But this is something that looks nice in the table. This is just e to the to the 10t. So that's the missing function that I was looking for. So then we can finally answer the question. So the inverse Laplace transform of what I started with, what I was really looking for, is really the shift of this function I figured out by 3 times the unit function starting at 3. So now all I have to do is take g, which I just figured out, and plug in t minus 3. And that's the answer. Okay, so I think we can streamline this process a lot more. It sort of got a little circular there, and I think made it a bit more confusing. This next example will help a bit. Oops. Gotta have my E in there. So again, the idea is if you spot an exponential to the power of negative something s, you should immediately be thinking that we're in this unit step function section. And then let's write it in the front, just because that's how we're used to the formula. S over s squared plus 9 is the rest of it. Okay. So then the idea is what we can do is immediately say that the inverse Laplace transform has to have the step function corresponding to pi, starting at pi over 2, because of this exponential being e to the negative pi over 2s. So it must have come from this times a function shifted over by pi over 2. And then what we know is that this function, we know its inverse Laplace transform is this stuff. So this is another one that's in our table. This is cosine of 3t. It's already in the nice form. So I figured out my g of t. So now I just plug in t minus pi over 2 instead of just t. And that's the end. Oops, that looks crappy. Let me rewrite that. T minus pi over 2. Okay, so that's the idea about calculating these inverse Laplace transforms for these shifted functions. The idea is you see that there's this exponential, so you know that there is some function who's been shifted by that amount, and that you took the Laplace transform of that thing, but you just don't know that function. And to get it, you're just doing the inverse Laplace transform of the rest of the stuff. And this is all because of the formula that the Laplace transform of the unit step function times a shifted function by that same amount is e to that negative cs times the Laplace transform of that function. So we're really just using this rule in reverse. So we're saying that because of this, that the inverse Laplace transform of something of this form equals the step function times the shifted amount. And so what we're doing is we're starting off with something like this on the inside. That's what's going on there. And we're saying, okay, I automatically know according to this formula that it looks like that times some g of t minus c, where this piece is this other stuff that's next to the e. So in this case, it was s over s squared plus 9. And so that is what allows us to solve for g as the inverse Laplace transform of that stuff. Okay, it just takes some practice. All right, let's do another one. This one will be a little bit bigger. I should have kept track of time. I feel like this is going on for a while, so I might not get to do the application I want. We shall see. Maybe I'll just stick it in the next lecture. Okay, so let's find one that's not already in the nicest form. So se to the negative 2s over 3s plus 2 times s minus 2. So again, you should be spotting this e to the negative 2s, and then you should be writing that as separated as possible from the rest of it. And so then the idea is we automatically know, because of how the Laplace transform works with step functions, that this is the step function starting at 2 times some function shifted by 2, where the function that's shifted by 2, we don't know, but we do know that its inverse is that its Laplace transform is this stuff. So to figure out g of t, I need to be able to do the inverse of something like this. But here we need partial fractions. Anytime you see something like this, you need partial fractions. So what you're going to do is try to figure out how many a's over 3s plus 2 plus however many b's over s minus 2 this is. And I'm not going to do the work here, but if you do it, you'll end up with a equals 1 over 4, b equals 1 over 4. So save time in all these Laplace transform problems. You should not be doing too many partial fractions. You can just use a calculator on Google, and it'll do partial fraction decomposition for you. So that's what I would recommend. And then we're going to write this as 1 over 4 times. And the reason I want to do this is because these types of things are exponentials. They're Laplace transforms of exponentials, because remember, e to the at becomes 1 over s minus a. That was the formula. So I really want to write these as 1 over something minus s minus something. So I'm going to also factor out a 3 here. So this can be s plus 2/3. And then b is 1/4. Down, this one is already nice. It's 1 over s minus 2. So now I can figure out g of t. So it's the inverse Laplace transform of this newer thing, which is slightly easier to deal with, or actually much easier to deal with. I can actually do it. So the inverse Laplace transform is 1/12. You can just take out e to the negative 2 over 3t plus 1 over 4 e to the 2t. So then now I know my g of t. I can go back and plug in t minus 2 and multiply it to here, and that's the answer. So let me just rewrite it here. So it's u2 of t, because I'm shifting by 2, times 1/12 e to the negative 2 over 3. And now I've replaced t with t minus 2. So 1 over 4th e to the 2 times t minus 2. And that's the Laplace transform of that. Okay. All right, I will do an example now. Let me pop it in. It's going to be a word problem. Okay, so we are back to spring problems, but now we have a much more interesting external force is the idea. So the setup is that we have this weight stretching the spring, but now we have an external force that only acts on the spring for 5 seconds. And then it's taken off. It like falls off or something. So it just stops acting on the spring. See if we can still do what we used to. In this situation, we're also going to assume that the spring starts from equilibrium with no initial velocity. So really the external force is what gets it going. We don't add anything extra. Okay, so it's still the same spring formula that we're used to, but there is no air resistance, so B is going to be 0. K and M I can figure out pretty quickly, but then my external force, I have to use a step function to properly describe it. So the idea is that it's 20t, but only for 5 seconds. So if I have a graph of 20t, it looks something like it's just a straight line. But if I want it to stop after 5 seconds, then what I can do to make this happen is I can use a step function. So it really looks like this, and then it just drops off. So what I can do is I can take 20t and I can subtract 20t. So that just give me 0, right? Well, I don't want it to be 0 all the time. I only want it to be 0 after 5 seconds. So this use of 5 will flip the second 20t on after 5 seconds, and I'll get 20t minus 20t is 0. So the rest of the time it'll be 0. So that's going to be my external force. K and M we could figure out using this 32. So let's see. 32 equals K times 2, because it stretches 2 feet. So K is 16. And then I need M. So M times 32, gravity is also 32 feet per second. So M is just 1. So this is the equation. Whoops, why did I add a sign in there? Okay. Okay, let's do this. So this is the type of thing that Laplace transforms really help us solve. So what we're going to do is we're going to take the Laplace transform of both sides, and because this is a initial value problem, that's going to really speed up some time because I don't have to find C1 and C2 and all that stuff, because I can just plug these in, and that's what the technique, that's what using the Laplace transform helps us speed up. Okay, so I Laplace everything. So, whoops, there's no prime on that one. And then on the right side, I can also start using the linear property right away. So I can just take that 20 out. I can take out 20 out of everything, in fact. Yeah, let's do that. And then I'll write this in this order. Okay, on the left side, remember that the Laplace transform turns derivatives into multiplication by the variable s. So this is going to be s squared times the Laplace transform of the mystery function p minus s times p of 0 minus p prime of 0 plus 16 times the Laplace transform of p. And then on the right side, I can calculate some stuff. So the Laplace transform of the variable t is 1 over s squared, if I remember right. And the Laplace transform of something like this, well, I need to, first of all, make sure that the function is shifting over by 5. So what I'm going to do is I'm going to subtract 5 and add 5 to make it be the same. So now this is the function f of t equals t plus 5. And I'm plugging in t minus 5 to get it back to being t. So now it's of the right form that I can use my new Laplace transform technique. So what is this going to be? E to the negative 5s, because it's shifting by 5, times the Laplace transform of t plus 5. Because that's the function that's being shifted over by 5 to the right. And that we can figure out because it's just going to be the Laplace transform of t plus 5 times the Laplace transform of 1. And whoops, too many curly brackets. And so one step at a time, s squared. Laplace transform of t is 1 over s squared. And the Laplace transform of 1 is 1 over s. Yeah, I'll just stick this underneath the 5. Okay, so that's the right side. The left side, luckily these initial conditions tell us these are both just 0. Save us a lot of time. I can just factor out this s squared plus 16 from the Laplace transform of the function I'm looking for. So then I can solve for the Laplace transform of the function that I'm looking for by dividing that over. So I'm going to divide it over in a very sneaky way. I'm going to keep this 20 just nice out in front so I don't have to worry about it. And then I'm going to stick the s squareds plus 16 on each piece. And I'm going to keep this 5s out because I know it's corresponding to a shift and I like it to be in that form already. So all I'm doing is I'm dividing this into each thing. Okay, so now how do I figure out the function I'm looking for? P of t. I now need to do the inverse Laplace transform. So immediately I can take out that 20 because I just left it there. So let's do that. And then I can separate through addition and subtraction like this. Lots of writing, lots and lots of writing. Okay. Now, Once again, we're going to need partial fractions, but we're just going to cheat and look it up. So if I do partial fractions on that thing, it'll end up with 1/16 as A and -1/16 as B. So you'll end up as 1/16 times 1/s squared minus 1/16 times 1/s squared plus 16. Notice that that's the same denominator here. So that's going to be the same partial fraction decomposition on that side. So that'll save us a little bit of time. So this is really 1/16 times 1/s squared minus 1/16 times 1/s squared plus 16. And then this 5/s business, you also have to use another partial fraction. So let's see, what is that? I looked it up earlier, so I wouldn't have to do it. This will turn out to be, what is it? Oh, yeah, 1/16 again of the 1/s's and minus, oh, it's actually the same. Interesting. 1/16 again times 5, no, oh, s, interesting, s/s squared plus 16. Sorry, my s's look too much like 5s. Okay. So that's that. All right. This 20 is on everything, by the way, like that. Whew, a lot of work. Okay, almost done. All right, so now we can do this Laplace transform, inverse transform. So the Laplace transform, you can take out the 1/16. Inverse transform of 1/s squared is t, just t. And the inverse Laplace transform of this is trickier. So the 16, I'm going to write as 4 squared. And then it's sine of 4t. If you look it up in the table, this will be sine of 4t. Okay, so that's that. Nice and done. Now here, it's a shift thing. So this is going to be a shift by 5 times the inverse Laplace transform of the rest of it is the idea again. Which I guess I can just call g of t shifted by 5, where g of t has the property that it is the inverse of all this stuff here. Okay, but we already wrote it in a form where it's easy to take the inverse Laplace transform. So starting from left to right, the inverse Laplace transform of that is take out the 1/16, 1/s squared just becomes t. Okay, I'll try to color code. This is, well, this is the same as what we just did. It's over here. 1/16 sine of 4t. And then this is 1/16, just 1/16 times 1. The Laplace transform of 1 is what gives you 1/s, if you remember. And then finally, minus another 1/16. This is actually a cosine, if you look in that table, of 4t. Actually, I'm missing a factor of 4 somewhere. I just realized. Yes, let's go back a little bit. Sorry. So that table requires there, for sine, requires there to be a 4 up here. So if I want to put that 4 there, I also have to divide by 1/4. So this is times 1/4. Same thing will happen over here. I really want there to be a 4 here, so I have to multiply by 1/4. And do I need that with the cosine? I don't need that with the cosine. So this one will have another 1/4 multiplied there. Well, 4 times 16 is 64, by the way, so that'll just be that. Okay, but that's my g of t. So now I just have to plug in t minus 5 to that g of t. All right, so let's simplify a little bit. 20 times t over 16 minus sine of 4t over 64 minus u5 of t times, now I'm just plugging in t minus 5, so this is t minus 5 over 16 minus sine of 4 times t minus 5 over 64 plus 1/16 minus cosine of 4 times t minus 5. Oh, there's also a 1/16 over 16. Okay, so that is the end there. Very big answer. If you graph this thing, it's actually interesting. So it basically looks something like this. And then after 5 seconds, it oscillates. Okay, I'm very tired. So that's the end of this lecture. See you later.